Thank you for the introduction, and thanks to the organizers for having me here. Today I'm going to talk about our joint work with colleagues from the Jade Hochschule in Oldenburg, a Fachhochschule. Reinhild Horden and Matthias Blau are acoustic engineers, and Nick Woolbush is my PhD student in maths, so he made a major contribution to this work that I'm going to talk about today. All right, so the topic is parameter identification of boundary conditions for acoustic applications. And to set up the stage, let us imagine we are in a recording room or in a theater, concert hall, whatever. And anyway, in some environment where good quality of acoustic signals is important. Okay, in such situations, you usually don't want that acoustic waves bounce out of the walls in all possible directions. You would rather prefer they are absorbed to a large extent. Well, usually walls are covered with absorbing panels in such case, and my aim for today will be to identify absorbing properties of such panels in a cheap and non-intrusive way. I don't want to dismount the panels. I don't want to do anything with them. I just want to put some loud speakers in a room, some microphones in a room, and some unstructurally randomly chosen positions, but reasonable positions, and use noisy measurements at microphones to detect material parameters or absorbing parameters of walls. All right, so here is the model forward problem. We are in the time harmonic setting, so the Helmholtz equation is governing the physics. There's an excitation by the loudspeaker on the right-hand side. And then we have two kinds of walls, or maybe floor and ceiling, two kinds of boundary conditions. Sound hard conditions in one part of the domain, for instance, here at the ceiling. We have a homogeneous Neumann boundary condition in this case. And on some walls or some other parts of the boundary, we may have an impedance boundary condition where that parameter, Z, the acoustic impedance, is to be estimated. So this is our goal, to have an estimate on that quantity. Well, for physical reasons, the real part of the acoustic impedance is positive, strictly positive, which basically means that the walls are passive and absorbing. Okay, and in this setting, it's well known that the problem is well defined, well posed. There's a unique solution, and a forward map as a map from the parameter space to the space of the solution to the complex pressure P is well defined. All right, concerning the source, I'm only going to use one loudspeaker. So the loudspeaker will be modeled as a point source, or the Dirac delta, located at some point S in the source domain. I call it the kappa, and this domain is well separated from walls of the room. So I don't want to put a loudspeaker directly at the wall. I want to have, say, half a meter distance at least. Okay, a reasonable location so that the sound can propagate reasonably in the room. By the way, various constants in the error analysis will depend on this kappa. They will also blow up if kappa tends to 0, say, and I'm going to assume for now that kappa is a fixed number. Okay, it's fixed in advance, which is a reasonable assumption. As I said, we don't want to put loudspeaker very close to the walls. All right, concerning the measurements or observations, recall S was my solution operator, then the observations can be seen, measurements can be seen as a composition of the solution map with an observation operator, which is, by design, a set of measurements at microphone positions. So there are point values of the complex pressure at locations x1 to xm that come from the measurement domain. I call it m kappa, and this one is assumed to be well separated from the walls and from the source domain. So I have kind of reasonable separation of where the signal comes from and where the microphones are, where the measurements are, please. It is time harmonic. It is time harmonic, so I have no time dependency. But we can run it for different frequencies that we will do later on. Yeah. Okay. These measurements are polluted by the noise, eta, that we will assume to be a multivariate complex normal. Okay, so this is how you can write down the density, and it's not difficult to see that this basically means that the real and the imaginary part of the of this complex random variable of the noise is actually a jointly Gaussian, two-dimensional Gaussian. Okay, so this is nothing fancy. This modeling has been used, by the way, in this recent work by Engel and co-authors. It could be that in practice, data will come in an alternative format. For instance, very frequently in acoustics, the amplitude and the phase are given, not the complex number. So you either recompute back and forth, or you have to tweak the noise model a little bit. Yeah, so it depends on the format a little bit. Now, having the bias theorem, you may immediately get this relation for the prior and posterior measures, or sorry, prior and posterior expectations, nu 0 and nu y. So this is the posterior expectation, which takes measurements into account. And our ultimate goal will be actually to get our hands on this posterior expectation. Now the quantities are, psi is the potential, theta is my notation for the likelihood, okay, and lambda will be the normalization constant. So this sort of expressions can be found in various works here, just a couple of them to name a few. Right, so what about prior? As I said, due to physical reasons, the impedance lives in the positive, or in a right complex half plane, right? Therefore, it kind of makes sense to put a prior that respects this condition. So we take a log normal distribution in a complex plane. Yeah. After some simple algebra, it's easy to figure out that this is the corresponding density for the prior. And well, then everything is actually set up to run the algorithm. Our goal will be estimation of the first two posterior moments of the expectation and the variance. Well, and then I also write approximate posterior and approximate mean. Of course, I do some numerical approximation, and this is on one hand due to finite element solve of the forward problem, and on the other hand due to plain Monte-Carlo approximation of expectations. So there's nothing fancy from the numerical point of view. It is a very naive approach, I would say, without any accelerations, but we will make some interesting observations in the course of the talk. Okay, having the first two posterior moments, you may actually also fit a density to represent the moments exactly. Of course, this will be not the posterior density. It will be some other density, but you still may see how it behaves for different values of the parameters. Yeah, and we will actually see that the behavior is quite reasonable. So what we are going to do, we will fit a similar log normal distribution to that two moments and observe what happens. So let me jump right away into results of the simulations in 2 dimensions. So with a simple toy problem, frequency is fixed to be 55 Hertz, quite low. Okay, and those are okay. So we are in this setting, this 2-dimensional setting with 2 absorbing walls, and they have different parameter values. the synthetic data come precisely from the impedance problem. So the data matches the model. There's no model data misfit. And let me see. Just fast. Okay, here are the reference values. They're not equal. Yeah, and this is what happens with the posterior or fitted posterior density, I should better say. Yeah, so you see it moves toward the reference value for the first wall and the second wall as well. Okay, the reference value is well in the support of this fitted posterior. And there's also concentration. Concentration can be observed as well. For one wall, it goes faster. For the other wall, the concentration is not yet pronounced. Yeah. If you increase frequency, then what you observe is that the picture basically is similar. The posterior density moves in the right direction to the value of the reference parameter, and the concentration is more pronounced actually in both cases. Yeah, which is kind of an interesting observation. You may also check numerical convergence with respect to the mesh size of the finite element solver and with respect to the number of samples. And here you observe kind of thing that you would expect to see. So the first moments for the first and second moments, mu and sigma, for the first and the second wall, okay, they converge at this quadratic rate, I would say, h squared. There's also an logarithm that I will justify in a moment, okay? So for reference purposes, there's a dashed line, which is h squared times the log, and you see the first and the second moments, they are basically parallel, the real and imaginary part as well, with that line. Checking the convergence in terms of the number of samples, you observe a standard Monte-Carlo approximation rate of 1 of the number of samples. Okay, this is how a reference solution would look like. Again, this is 50 hertz example. A loudspeaker over here, some microphones in that positions, and you see for this low frequency, we recover the reference solution actually extremely well. So I actually cannot see optically a difference, yeah? Which is actually not obvious for a problem with wave phenomenon. Of course, I should say the frequency is low, and as it rises, things become tricky. But this is already good news, I would say. So for the remainder of the talk, my aims will be then to explain the convergence behavior that we have just seen with respect to the mesh size and with respect to the number of samples for that particular application. And then look in a more realistic setting, check the three-dimensional situation and try to understand what is the impact of the data model misfit. So what will happen if the data, synthetic data, will come from the model that is not absorbing at all. So we will try some non-locally reacting boundary conditions in this part. Okay, so let me comment on theory very quickly, because we can actually treat this example with some minor modifications by classical already known results. The source on the right-hand side is Dirac delta. That's why the weak solution does not exist as a function in H1. We need to do something else, and there are different ways to treat this situation. One possible way is to go to the so-called very weak or ultra weak formulation, where you essentially integrate the weak form by parts once again. And then the Laplacian, all the derivatives, they are at the test function. You look for the solution P in L2 that satisfies this formulation for all test functions in a smoother space. Okay, and then it is not very difficult to show that this problem is well posed. It has a unique solution for any location of the source in the source domain. And moreover, the solution is smooth in the measurement domain, where we care about the point values. So we are interested in locations where the microphones can be, or in the measurement domain only. And well, this domain has been separated from walls and the sources. That's why the solution is regular over there. Okay, and moreover, I claim that the point values of the solutions are Lipschitz continuous with respect to the impedance parameter Z, basically that this sort of bound holds true. Quick sketch of the proof, quite standard. You write down the solution to this source problem with a Dirac delta on the right as the fundamental solution plus the rest. Okay, so the fundamental solution takes care of the singular source. The U will not have a singularity due to the source anymore, but it will have modified boundary conditions. Okay, so for this reason, this U will be smoother and will exist as a solution of a weak formulation, of a weak problem, as a function in H1 in the domain D in the room. For such solutions, room was convex, so we have H2 regularity of the U part of this auxiliary function and corresponding H2 estimates for the U in terms of the boundary conditions. Okay, so we are interested, if we are about to prove the Lipschitz continuity, we are interested in the difference between the solution for one or the other impedance. So in this difference, if you now plug that representation into the norm on the left, you see that the fundamental solution cancels out and only the difference of the auxiliary function remains. And here we use H2 regularity bounds for the difference between solutions. And this is the right-hand side. And well, basically it gives the statement. So the left-hand side is an upper bound for the point values by Sobolev embedding theorem, okay? And on the right-hand side, we have some boundary norm of the fundamental solution located with the singularity well separated from the boundary path. The fundamental solution is smooth. And what remains is 1 over z, the function 1 over z, which is Lipschitz continuous away from 0. And we're done. So, okay, in particular, from that property, we are sure that the solution is a well-defined random variable. So it's a composition of a continuous map with a measurable map with respect to the measure on Z. Okay, so this is a well-defined random field. All right. Concerning discretization, we now discretize with plain linear continuous finite elements. For this, we can take the plain symmetric variational formulation. We don't have to go very weak, because now the right-hand side, the Dirac delta in the right-hand side, if you test it with a continuous basis function, you have a point evaluation. Okay, so this is now a well-defined thing. And we are interested in the mismatch between the true values of the solution in a given point and the value of the discrete solution in the same, precisely same given point, which is basically an L infinity error estimate for the finite element method, which is a classical thing as well. Okay. If you look for precisely this result for the acoustic applications, this goes back to the work of Rodriguez and co-authors, and can be also found in the work by Engel, 2019. Okay, so this is a settled thing, well known in the literature. Now, if we know about the error in the forward map, this translates immediately to the corresponding bound for the likelihood, because the likelihood is a smooth function, as somebody mentioned today already. Jakob, I think, had a comment on that. Likelihood is a smooth function. That's why. So basically, you do Taylor expansion. You may argue with the Taylor expansion and carry over the error bound, and this controls the bias of the estimator. Yeah, the variance of the estimator can be treated in the usual way, as an estimate, standard estimate for the Monte-Carlo method. So if you put everything in the framework of the paper by Rob, 2017, for the root mean square error, estimating the bias part and the variance part, you get the standard sum of error contributions, statistical and deterministic error contributions. Okay, and if you look at the examples that we have just seen, this is precisely the slope of the curves here and there. So there's a kind of more or less standard explanation also in that particular application of the convergence of the estimators. Now, let me look into 3D and see what happens there. First of all, let us check the case of locally reacting walls. So this is basically the same setup. I have a room now in 3 dimensions, and I have walls that are absorbing. And now for simplicity, let me assume that one of them has known parameters, known absorbing parameter values. They will be fixed. And we will only determine parameters, impedance coefficient for the wall gamma 2, which has now somewhat different value and will be determined by Bayesian inference. Okay, let us look at the likelihood. So here I have many lines. Every line corresponds to another microphone configuration. So I have many of them. They are chosen randomly. I don't really know what is the best configuration. There are also some issues with symmetry. So you don't want to put microphones in a symmetric way, for sure. For different microphone locations, can be lucky, maybe unlucky. So you have different values of likelihood, but none of them goes very dramatically down. Of course, there are some very relatively small likelihood values, but there are also very lucky microphone positions where you get good high likelihood values. All right, there's something strange going on here. Maybe for that particular frequency, that particular microphone configuration is extremely unpleasant, yeah, or undesired. This is raw data. Now, if you continue checking what is going, this was over the frequency band from 20 Hertz to 120 Hertz. So we can actually choose a window and run the code in a certain interval. Now, what happens if we look at the best parameter fit, best impedance fit to each selected density? Okay, so then the curves will wiggle even more, especially for low frequency values. But as long as you look at the mean, as long as you average, you get actually quite a reasonable estimation of the reference. So this thick red line actually is not too far from the reference, which is a dashed line for the real part and the imaginary part of the impedance. So I see it as actually as a successful identification of a reference value in that particular practical problem. So it goes. So what is about fitted posterior densities? We actually observe a similar behavior what we saw in the 2D case. So there's a tendency movement towards the reference value, and when the frequency increases, the concentration is large, is more pronounced. Okay, reference value is well in the support of the posterior density, which is of course very important. Okay, so this was for the case where the model was consistent with the data. Now we do something, well, forbidden in mathematical sense, but very natural in practice, because we of course don't know how the walls react. Yeah, we may model them with some boundary condition which is more complex or less complex, but we never can capture the physics of the wall exactly. So now let me assume the following. Now gamma 2, this red part, will be modeled as a wall of glass, a large window, say, which is an object that doesn't react locally. If you excite it at one point, you hit it at one point, it will oscillate everywhere, as opposed to absorbing local boundary conditions. So if you put a wave, it only acts in that particular point and has no impact to the neighbors. So this is a very different behavior of the boundary. Now what we will do in this setting, we will take synthetic data generated by some commercial software, COMSOL multiphysics, for instance, in this case. They have implemented these models, and in the background, it is a coupled acoustic structural simulation in the background. Okay, so there's some thin shell or whatever model for the window, I suppose, some mechanical model with material parameters that are taken for the glass. Okay, not so important at that moment what this model precisely is. We have a black box that behaves differently as our forward model. Right, so we have a model data misfit, since our forward model will still be the impedance problem. So let's see what can we find in this case, and can we trick the physics. So this is what comes out in terms of the maximum of the likelihood for different frequency values. So you see a very different picture to what we had before. No surprise, we try to identify a wrong model. Okay, but what is striking, in my view, is that there are some frequency bands where the agreement is actually quite good. So for some frequency bands, the misfit between data and the model is essentially invisible. So like here, for instance, between 35 and 50 hertz, between 22 and 35, and also in this regions, and for instance, also for reasonable frequencies, for higher frequencies between 90 and 100, the algorithm says, oh, I have a good impedance absorbing impedance boundary condition for you. Yeah.
You still have damping or absorbing solutions?
Yeah, the model is the same as in the first example, as in here. So I have a wall, okay, so another wall that is damping.
You don't have a real resonance system?
No. You will see in a second. All right. Okay. Whereas in the other cases, and for some other frequencies, the likelihood goes down dramatically, and for all microphone positions, for all 20, or I think we took 20 in this picture. So in this location, the coupled problem and our wrong forward problem, the impedance problem, they seem to behave very differently. For some frequencies, they are kind of similar in the interior of the domain. For the others, they are different. And to be able to understand what's going on, let us look at eigenfrequencies, what Fabio suggested. So here I plot a number of them. Important are red crosses. So red crosses correspond to eigenfrequencies of the coupled problem. They are all, there are no purely real of them, yeah, but there's a cluster near the real axis. There's a cluster near the real axis. There's also this fan above, yeah, with large imaginary part, and also an interesting cluster in the middle regime, but those will be important, yeah. So let's understand, what are they? What are those eigen frequencies with low imaginary part? For this reason, let us look at the eigenfrequencies of the window only, which the software package can still compute. So it has to impose some boundary condition. I suppose that there will be traction-free boundary conditions at the boundary of the window to compute this eigenfrequencies. They will be purely real, okay? And what you observe is actually, they are small shifts of the red crosses, or the other way around, if you look at the real part only. So the coupled problem takes over eigenfrequencies essentially from the window part. Window has a big influence on what is going on in the volume, and yeah, somehow this may impact the outcome of the coupled simulation. All right, so let us now combine that with a picture of the maximum likelihood. So that was the picture that we already saw, and now I will put the frequencies on top of them. Okay. A lot of things going on in this picture. Let me draw your attention to the following. So if there's a frequency drop at some maximum likelihood drop at some particular frequency, then for sure there's an eigenfrequency nearby. So for instance, in this region, there are eigenfrequencies nearby. Here in this region, there are eigenfrequencies nearby. Here's a gap. There are no eigenfrequencies with low imaginary part, and also no drops of the likelihood. But not everywhere. For instance, there are some locations like, let me show this one, for instance, this small window between two dramatic drops. There are some eigenfrequencies with very low imaginary part, but the algorithm can fit an impedance model very well to that situation, which is kind of surprising. Yeah, so you have kind of a strong oscillation of the window, but you don't see it in the interior. Why? So let's zoom into it and check some particular solutions. Maybe we'll see the answer. So I have just taken three typical situations, three typical values, and those are sitting. The first one is sitting here, just in the middle of this extended region with dramatically small maximum likelihood values. The other one, 34, it will be in the next interval where the likelihood is actually very big. So where the algorithm says I can fit the impedance problem, okay? And then the other one will be at 69 hertz. It will be somewhere here where this not very well pronounced drop occurs, yeah? So for some microphone positions, you have kind of poor match. For the others, yeah, you also feel that there's a drop, but not so pronounced as in the other location. So let's see what happens. So this is the picture for the first situation where we had very low maximum likelihood, and this is the solution of the couple problem. That is the impedance problem, the best fit. And what you see, of course, the solutions are different at the glass wall. So this is the wall facing at us. Okay, these oscillations are glass oscillations, but also in the interior. So these oscillations, they extend, they continue in the interior, and the solution in the interior is very different as well. For instance, there's a maximum in this distant corner in the impedance problem, whereas it looks very different in the other situation. So solutions are indeed very different in those two different cases. And now, let me turn to this gap where you would actually expect a poor correspondence, but you don't see it. You have a good likelihood, right? The solution may look like that. So at the glass wall, there are some oscillations due to, structural oscillations, but they do not go very far in the domain, right? So this is the impedance solution. This is the coupled solution. And what you observe that in the interior of the domain, the values are very close to each other. So I can actually, I would say, so optically, it's very difficult to distinguish them. So the impedance problem, the difference between the two, let me say, the difference between the two decays to zero very quickly as you go away from the glass wall. Okay, and this explains why the algorithm can fit an absorbing boundary condition to the problem with non-absorbing physics. All right, and also there are some other cases here for some higher frequencies where in some parts of the domain, the solutions are quite different. For instance, this blue region is of somewhat different size. But if you look at the distant corner, for instance, the values are quite similar as well. So you may find, by chance, you may find a microphone position, configuration of microphones that doesn't fit or doesn't sense this critical regions, okay, where the mismatch is large. Okay, and this explains why you have somewhat not very much pronounced drop in the likelihood over here. Okay. Okay, here is what I want to share with you. So we have some observations on Bayesian inference. It seems to work well as long as there's no data model misfit. Yeah, at least in the low hearing range. This is the range that we considered, and you can do some basic theory, and also numerical examples confirm theoretical findings. Now, if the model data misfit is present and can be usually recognized by low values of the likelihood, if you check it for sufficiently large band of frequencies. Okay, if you check it just for a small band or some accidentally selected values, you actually can hit a situation where you don't sense the non-absorbing behavior of the boundary. Okay, so important is that the range is sufficiently large. Yeah, and for certain frequency bands, for certain frequency value, misfit will not be detected as we observed in the simulation, and this can be explained by particular structure of solutions. Yeah, the model, the window oscillates, but this oscillation is actually localized to the wall. It's still non-locally reacting, but the effect doesn't propagate the interior of the domain. Okay, that's it, and thanks for your attention.